This video describes POEM, our tool for pattern-oriented explanations of convolutional neural networks. POEM is an example of a explainable artificial intelligence tool. As input, it takes in two things: a pre-trained convolutional neural network for image classification, and a target dataset that contains images that the CNN was trained to classify. As output, POEM produces a set of rules linking concepts that exist in images with the model's decisions. For example, POEM might produce a rule that says if bed, then bedroom. This means that if an image contains a bed and the model paid attention to that area of the image during inference, then the model classifies the image as a bedroom. To create these rules, we follow a three-step method. Number one, we identify concepts that exist in images. Number two, we identify concepts that not only exist in images, but also the model paid attention to during inference. Finally, we mine rules linking the concepts with the model's decisions. Let me first describe concept identification. For every image in the target dataset, two things happen. On the right of this illustration, every image is passed through an external semantic segmentation model. So POEM requires access to a segmentation model that can identify semantic concepts in images, such as shapes, colors, textures, and so on. So the output of the semantic segmentation model for every image consists of potential concepts that may exist in the image and where those concepts are located. Furthermore, for every image in the target dataset on the left-hand side of this image, we pass it through our CNN model under investigation, and we inspect the activations of every filter in the CNN. So at a high level, a convolutional neural network consists of a set of layers, and within each layer, there is a set of filters. And these filters, with weights that are trained during backpropagation, are meant to identify various shapes and concepts in images. The first layer might identify simple shapes like lines. The final convolutional layer might identify more complex images like beds or faces. So we focus on the filters in the last convolutional layer that are expected to identify interesting and complex concepts. So each of these filters has an activation map identifying the pixels in the image that this filter paid attention to the most. So in this example, the yellow pixels are the most highly activated areas of the image for this particular filter. We then take this filter activation map and superimpose it onto the image. That gives us the location of the image that this particular filter seems to have paid attention to. We then take those areas of the image and identify any overlapping concepts that were identified by the semantic segmentation model. If there is sufficient overlap, and if this overlap occurs for sufficiently many images, then we might conclude that this particular filter happens to identify this particular concept, such as a bed. So at the end of the concept identification stage, the output consists of each of the filters in the last convolutional layer of the CNN and the corresponding most likely concept that this filter might identify from the space of concepts identified by the semantic segmentation model that we use in POEM. Next, we proceed to the concept attribution step. Once again, we take every image in the target dataset. On the right-hand side of this illustration, we repeat the semantic segmentation process from the first step. So for every image, we know the potentially interesting concepts that exist in the image and where they're located. Now, one simple way to attribute concepts to images is to say that in this particular image, a bed exists, and then our model classified this image as a bedroom as opposed to a kitchen or a living room. And that might be sufficient to claim that the concept of the bed was important for the model's prediction of this image as a bedroom. However, just because the bed exists in the image doesn't necessarily mean that the model paid attention to this part of the image during inference. So there's one more step that we add to the concept attribution step, illustrated on the left-hand side of this illustration. So for every image in the target dataset, we again pass it through the model. For every concept that was identified in this image, we then identify the corresponding filter from the previous step. So here on the left-hand side, we have the filter activation map of the filter that was mapped to the bed concept in this image. And then we take a dot product of the filter activation map with the gradient map of the model. And the gradient map comes from the very last layer of the whole CNN, where the probabilities of the different classes are computed. So in this example, our model classified this image as a bedroom. So we take the gradients of the bedroom class, take a cross product of that with the activation map of the filter, and what we get is a filter saliency map. The filter saliency map identifies locations in the image that the filter was activated on, and furthermore, that the model paid attention to, that were important for the model when classifying this image as a bedroom, i.e. when computing the probabilities of the different classes. Okay? And then we take this filter saliency map and compute the overlap with the identified concept by the semantic segmentation model. If there is sufficient overlap, then only then we conclude that the concept of the bed was important for this model's prediction of this image as a bedroom. It is not just the presence of the bed, it is additionally the gradient maps of the bedroom class. At the end of the concept attribution step, for every image, we have a set of 0, 1, or more concepts that were important for the model's decision-making on every image. And then we can include the model's predictions. And what we get is a data set with a set of concepts followed by the prediction that the model made for this particular image. And finally, in the concept rule mining step, we take this data set, so we take the output of the previous concept attribution step, and we mine the rules over this data set to identify patterns between the concepts and the model's predictions. For this, we use 3 rule mining methods. We use classical classification and regression trees, CART. We also use explanation tables and interpretable decision sets. We then score each rule generated by any one of these 3 methods according to the rule's coverage and accuracy, and we output the highest scoring rules to the user. And so as some examples of the output of the concept rule mining step might be if sofa, then living room, or if bed, then bedroom. Next, we show the POEM front end. On the left-hand side, you can choose a dataset and a pre-trained CNN model. Then you can choose which of the 3 pattern mining methods to use. Here we've chosen all 3 of them. Press compute patterns, and we get a set of rules or a set of patterns to explain the CNN. The first rule at the top here says if bed equals yes, then the prediction is bedroom. So if bed, then bedroom. The support of this rule is 0.19. This means that 19% of the examples in the target dataset have the concept of the bed and were predicted by the model as a bedroom. The confidence of this rule is 0.99. It says that out of all the images where the concept bed exists, they were classified as bedrooms 99% of the time. The accuracy of this rule is 0.99. This means that out of all the images that contain beds and were classified by the model as bedrooms, 99% of them are actually labeled in the target dataset as bedrooms. Okay? And then the score of 0.19 is a combination of support confidence and accuracy with the details of the score computation presented in the paper. And then we show which method the rule came from. Okay? Then for each rule, we can illustrate matching examples. So for rule number 1, matching examples are those that are images that have beds and were predicted as bedrooms. We can also show non-matching examples. These would be examples of images that have beds, but were predicted as something else besides a bedroom, maybe a kitchen. And finally, we can output wrongly predicted images. For rule number 1, those are images that contain beds that were predicted by the model as bedrooms, but have a different label in the target dataset, maybe a kitchen. So at the bottom of this illustration, we show the matching images for the first rule. So those images contain beds and were predicted as bedrooms, with the areas corresponding to beds highlighted. Finally, let me give you some examples of how we could use non-matching or wrongly predicted examples to identify model weaknesses and potential data quality problems in the target dataset. Let's look at the leftmost image. This image is a wrongly predicted example for if sofa, then living room. So this means that there was a sofa there that the model paid attention to. The model predicted that it's a living room, but it was labeled as something else in the target dataset. Specifically, the leftmost image was labeled as a bedroom in the target dataset, even though it was predicted as a living room by the model. When we look at this image, will we notice that there is in fact a sofa there, and it looks more like a living room than a bedroom. So this could be an example of a mislabeled data point or mislabeled example in our target dataset, rather than a model quality issue. The rightmost example is similar. There is a sofa there, and it looks more like a living room than a bedroom. So the model predicted it as a living room. It's labeled as a bedroom. Maybe it should have been labeled as a living room. So maybe this is a data quality problem, not a model problem. On the other hand, for the two examples in the middle, they're also wrongly predicted examples. So the model says there's a sofa there. Therefore, the model predicts that this is a living room, but those two images are actually labeled as bedrooms in the target dataset. And the alleged existence of the sofa concept is highlighted in these images. So those areas don't look like sofas. In this image here, this looks like a bed with a stack of pillows on top of it, which may resemble sofa cushions. In this image here, there's a bed with a blanket on top of it that might resemble a sofa. So in both of these examples, this looks like a potential weakness of our model. In some cases, in practice, as shown in our target dataset, there may be beds with stacks of blankets or pillows on top of them that look more like sofas than beds. To help the model, it might be useful to collect more examples of these different kinds of beds to make sure that the model can distinguish between beds and sofas properly.